And when you find the overall chemical equation, you do need to know what is the cell potential. So that's where we use the table. Every one of these problems, just like in the last couple of chapters, the buffer chapter, every problem you had to find the pH, right? Find the pH if we add this much base to this buffer. Well now, every problem you're going to have to find the cell potential. So you'll be running to that table every problem that you do. So for a complete description of a cell, component number 1 is the balance equation and the cell potential. It may not be in standard conditions, so that may or may not be true. And then component number 2, in your drawing, and you will have to sketch the cell, you have to know what direction the electrons are flowing through the wire. Are they going from left to right, or are they going from right to left? I'll always draw my cells with the anode on the left, and that's where the oxidation occurs. The electrons always flow from left to right. In the ones that I draw. 5. There's 5 components here.
Except for the reading.
Yeah. That'd be the only time. But I don't feel bad about that because you didn't get used to anything yet. Okay. The third thing is, you always need to identify which compartment has the anode and which compartment has the cathode. We talked about anode and cathode last time, right? Which is which? What process is happening at the anode? Did you say that right, Patrick?
Yeah, cathode is reduction.
Oh yeah, okay. Yep. Yep. Anode oxidation, 2 vowels. Cathode reduction, 2 consonants. That's how we remember that. Now number 4 is loaded.
Oh, jeez.
We're going to have to know what each electrode is. Electrode is the metal bar that's sitting, like in this case, zinc is an electrode and copper is an electrode. It's not always obvious what electrode you use. And so that's why this is so wordy. So in our description of a cell, we need to know what electrode gets stuck into each solution. There's going to be 2 solutions, 2 compartments. If your reactant or product is a metal, then that metal becomes your electrode. Sometimes, though, you don't have a metal as one of your reactants or products. And that's what I'm saying down here. In that case, you have to use some inert conductor, like very common as platinum. Don't blow your nose into the microphone.
Who's sick?
What's that?
Who's sick? Who's gone?
We have Whitney in 3rd hour, and I think somebody in 1st hour was absent too.
Oh, it's other people from
Yeah.
our class. Shoot.
Yeah.
So it's not our fault?
I think we're all here today.
Where's the grenade?
Gotta make like a sign that says my bad or something.
You can just say it out loud, Raul. That's
Oh, but it seems more professional.
fine. There's a minor little issue with using platinum. You know what it is? Yeah, platinum works great. I'd love to have lots of platinum electrodes. Unfortunately, it's very expensive. We actually do have, we've got a couple of demonstration setups that have little platinum leaves in them. They're very thin, very minor amount of platinum, and still they do drive the price up of those setups. But
More than fluorine?
I don't know. I've never had to buy fluorine. I don't know how expensive fluorine is. I think it probably is though.
More
Platinum is one of the
expensive
most
than like,
expensive materials that you can buy.
more expensive than like carbon?
Carbon's not expensive.
I know.
Speaking of carbon, rather than using platinum in here, we'll wind up using, if we need an inert conductor, we'll use graphite. In this graphite, it's the real thing, yep. This is just like a pencil lead. It is a pencil lead, but it's about the diameter of a full pencil. This is poor man's platinum. It works great. It doesn't dissolve or corrode. When I'm talking about using platinum in here, really we'll be using for real this stuff, okay? So if I use this and I call it platinum, don't correct me, okay? It just makes me feel good. Oh, well, take out your platinum electrode, right? And use it. We're allowed to if we were, you know, a highfalutin university or whatever, we'd have real platinum. But
Darn, I would have
we're
stolen
high
it.
school.
Wait, does the gear sound like all dirty and gray?
No, no.
Oh.
There. See, it works. Okay. So that was part number 4, is we have to know what each electrode is. Again, if one of your components or compartments has a metal as a reactant or product, then just use that metal. Like in this case, it was zinc changing to copper, and so you have zinc as your electrode there, and copper as your electrode there. But if I can go back, remember this reaction that we talked about before. This was the zinc and hydrogen. Just go back where it described. Yeah, this reaction right here, the oxidation of zinc and the production of hydrogen bubbles. On Monday, so messed up on the days. On Wednesday, I talked about the zinc hydrogen reaction, and this is the sketch of that cell. So for the zinc half reaction, you use the zinc bar. I didn't talk much about it for the hydrogen side though. Since it's hydrogen, the ion changing to hydrogen gas, you don't have a metal as a reactant or product, so that's where we use platinum. Okay?
Certainly not graphite.
No, no, no. That's for the low class people.
Yeah.
Plebeians.
For the common people. All right, now for our
That
copper
should
iron
actually be
reaction,
something.
this is the one we're kind of focused on today. We also have another way that chemical equations are written, a notation for electrochemistry. It's called line notation. This is a simple one, and we'll start simple. Line notation separates the anode from the cathode. It kind of describes what's happening in the anode compartment and what's happening in the cathode compartment with special symbolism. The single line there separates physical states or phases. You've got the solid iron changing to iron ion. That's what happens in the oxidation in the anode. Over in the cathode, we have copper ions reducing to neutral copper. That's what's going on in the cathode. So the signal line represents a different phase. Physical state kind of phase. Like in this case, you have solid changing phase into aqueous. Over here we have aqueous changing phase into solid. The double line represents the salt bridge. So that changes, that separates the two compartments. Now it's pretty easy if we have a compartment that has a solid electrode. Well, they always have solid electrodes, but a reactant or product as an electrode. Sometimes though, like in the zinc hydrogen reaction where you have to use an inert electrode, be aware that the first thing in the anode must say what the electrode is And the last thing in the cathode must say what the electrode is. So the electrodes are always the terms on the outside. For the case of the zinc-hydrogen reaction, this is what the line notation will look like. This is a little bit different. You've got to train your brain on this one to know like what that means. This part over here is the cathode. That's the reduction of hydrogen ions to hydrogen gas. And even though aqueous is a different phase than gas, we have to say what the electrode is on the very end of it. This has to be the electrode. The zinc bar was the electrode on the anode side. But over here, the electrode in the cathode side is platinum. So on this side of the single line, you have to say what it started as and what it ended as. So line notation can be a little bit confusing. We all good? So only really one other thing what I'd like to do today, and that is do an example. At the beginning of the exercises in this chapter, you're going to have big lines, and please don't, this is like 5 lines of things that's telling you what to do. You'll take the rest of the hour to write the problem out. Don't write the problem out. We'll do lots of these, and you'll have to go back and do several in the exercises. I guarantee on the quiz on this chapter, there will be a question just like this. I'll change what the chemical equation is, but I'll ask you to sketch a cell and label the direction of electron flow and say what the anode and cathode are and give the overall balance equation, all those kinds of things. So there will be a question like this. Make sure that you don't blow off the exercises that include these, because one of those is going to be on the quiz, for sure. So I'd like to go through and do this one with you. Sketch the galvanic cell based on the following overall reaction. And here's our overall reaction in number 36B. This one is pretty simple. We'll start simple, and then on Monday when we get back, I'll review this one with you, and then I'll ask you to try one. All right, so show the direction of electron flow. So anyway, what's oxidized and what's reduced here? Who will be at the anode and who's going to be at the cathode? Go ahead.
Ag is being reduced.
Ag is being reduced, going from positive
It'll be on the
to
cathode.
neutrals. That's on the cathode side. The zinc is oxidizing. So I'll need 2 compartments.
Hi, Mr. Moore.
Isabel, hi.
How are you?
I'm great. Nice to see you. Thanks.
I'm watching.
Doing electrochem. You remember those days?
No.
Come on. We have a salt bridge. Always include your salt bridge. I'll be looking for your salt bridge. In fact, it says something about the salt bridge in the problem, so you can't not remember to do that.
2 potatoes being stuffed.
We're going to need 2 bars.
You don't know the definition.
Floating? Floating metal bars? Yeah, we always write it like that. All right. Now this one, again, I always put the anode on the left and the cathode on the right. Come on, Isabel. This has got to come back to you a little bit.
Well, didn't we use a grapefruit?
Yeah. Yep. And we have the potato cock today. So at the anode, we decided the oxidation was occurring. That's where the zinc is becoming Zn positive too. So our metal over here is Zn, and the metal over here is silver. Okay? Now, what is the direction of electron flow?